Today what I want to do is to talk about contacts to semiconductors. This will lay the foundation for talking about other devices like p-n junctions and transistors and so on. And the question arises, for any kind of device, how do we get current in and out of the device? So we've got to have some kind of a contact that allows us to do that. And there are two kinds of contacts that we can talk about, and one is an ohmic contact. Okay. And the basic idea behind the ohmic contact is that it does not distort or limit the performance of the device. It simply serves as a means for getting current in and out of the device without the contact itself being the limiting factor. And as the name implies, the characteristics of these contacts in terms of current versus voltage will be linear. Now, strictly speaking, in a real contact, that is not true, or may not be true, I should say. You may have some degree of nonlinearity, but the main point there is that is the contact resistance, that means the resistance that the contact offers to the passage of current through it, insignificant. Because otherwise that will become the current limiting factor rather than the device performance itself. So those are what are called ohmic contacts, and I will come to that later simply to say it's a means of getting current in and out of the device without affecting the performance of the device. Okay? That's basically what an ohmic contact is. Now, an ohmic contact, therefore, by its definition, is required for all devices, because in all these devices I have to get current in and out. So in terms of application, where do you use an ohmic contact? Everywhere, in just about every device. Schottky contact, on the other hand, is a specific case when we have evaporated the metal onto the semiconductor, just as for an ohmic contact, except that the behavior of this contact is very, very different than an ohmic contact for reasons that we will see shortly. We will see that actually the contact has got rectifying behavior, and so its applications include rectifying circuits, photovoltaic devices, and so on. We will come to that, why it is used. Basically, other names for this are Schottky junction or Schottky diode. And later in our, after I have had a chance to discuss p-n junctions, we could probably make a comparison between p-n junction and Schottky. In many ways, they are similar, and yet there are some significant differences between the two. And so we can come to that when we come to p-n junctions in a few lectures, or maybe in a next lecture, maybe. So what I'd like to do today is to deal with a specific case. We've got some metal which is evaporated onto an n-type semiconductor.
Sir, direction of current also distinguishes this Schottky contact and Ohmic contact. In Ohmic contact,
Yeah.
I may be right or not. In both directions current can flow, and Schottky contact.
That's exactly what I said. Rectifying, the word means it allows the flow in one direction but not in the other. Right? That's the meaning of the word to rectify, as used in this context. Rectify generally means to fix, but in this case it means it allows in one direction and not in the other. So we'll see why it does that. And an ohmic contact, as I said, the characteristics are linear, which implies that it allows it in both ways. You're correct. So we've got some kind of an evaporation of a metal onto an n-type semiconductor. You could do the same argument with a p-type semiconductor too, and the essence of the argument is essentially the same. And what we do is we begin by looking at the contacts before they are brought into before the two situations, one where the metal is not yet into contact with the semiconductor, and the other case where it is already in touch. And the specific example that we'd look at is where phi m, which is the metal work function as we've seen before, okay, we define the vacuum level up there, where the electron is essentially free of the metal, of the solid, but has no kinetic energy. Kinetic energy is 0 at the vacuum level. It has just freed itself. It's got out of the system if it's there, but it's not. It doesn't have any kinetic energy. And this is the Fermi level of the metal. So what the situation we are considering is where phi m is greater than phi n, where phi n is the work function of the n-type semiconductor. And so in that case, before we bring them into contact, I've got the Fermi level the conduction band as before here. It's an N-type, so the Fermi level is there, and then we have the valence band. So this is the phi n from the Fermi level of the N-type semiconductor to vacuum. Remember, we had also defined chi from the bottom of the conduction band to vacuum level. We will make use of chi. So for a second, just use this. Okay. So here's the metal, and here is the N-type semiconductor before these two have been brought into contact. Now, effectively, what we have is the work function. It represents the minimum energy that is required to remove the electron from the solid. We had discussed that. And in both these cases, the definition is true, even though in the case of the semiconductor, there are no electrons at the Fermi level. Right? We have defined the work function, even in the case of the semiconductor, as from Fermi level to vacuum level. So even in this case, the definition still holds that is the minimum energy required to get the electrons out. The argument is a more detailed argument. It involves the fact that the semiconductor, if it's in thermal equilibrium, even though we are removing electrons from the bottom of the conduction band, in order to maintain equilibrium, some energy has to be absorbed to again bring back an electron excited from the valence band. So the sum total of all those energies, when you consider, effectively what we have is that the energy, minimum energy that you will require to get an electron out of the semiconductor to the vacuum level is still phi n, same as the definition for the metal work function. So here's a situation, phi m is greater than phi n. So that means in general, the electrons are sitting more energetic here. The Fermi level is higher than in this case, so the electrons have more energy here. And now when I bring these two together in contact with each other, which we actually do by evaporating the metal onto the semiconductor, we want to see what happens when we bring them together. Basically, electrons will tunnel from semiconductor to metal in this case. I'm going to use these abbreviations S and M, semiconductor to metal, because the electrons have got a higher energy here compared to here, so they'll want to come down here. And when they do that, we'll come to the final sketch, they start accumulating in the metal here. Okay, we've got electrons coming here. So this area is getting more and more negatively charged with respect to the earlier neutral metal. On the other hand, it's leaving behind in the semiconductor a core of positively charged ions. So you're increasingly leaving behind larger amount of positive charge, and so a field is set up from this side to this side. There's positive charge which will try to attract back electrons, and then there is this energy difference which will cause the electrons to come in this direction. So finally an equilibrium is established between these two cases when we bring them in contact.
So where is the positive charge, in the conduction band or in the valence?
No, you can't show that in the conduction band or valence band. It is in the semiconductor. So I will not sketch it into the Venn diagram, but more if we do, I'll sketch that in a second. If we simply look at the semiconductor metal interface, I am drawing the metal thinner because typically the metal is orders of magnitude thinner than the semiconductor. There will be, in this interface here between the metal and the semiconductor, some region where there will be positive charges that are left behind. Okay? And then you have the accumulation of electrons as they have tunneled through from the semiconductor because of their higher energy. So a field is now set up in this direction, and when equilibrium is established, it balances the flow of electrons that were wanting to come into the metal because of the difference in the Fermi levels. And at the end of it all, as we saw earlier, the Fermi level gets equalized. Throughout the solid, the Fermi level must be the same, otherwise there will be energy left for external work to be done. So once equilibrium is established, equilibrium is being established because the field that is acting from this direction of the remaining positive charges towards the metal interface is able to balance out the field that is there, or the driving force that is there in terms of the energy difference between the electrons in both these materials. And at that point, the Fermi levels are equalized. So when we do this, we have a built-in potential in this direction. The field is in the opposite direction. This potential is known as the contact potential. So when we bring the metal into contact with the semiconductor, we develop a contact potential. It's also known as the built-in potential. And the field accordingly is known as the built-in electric field. So this layer that is created here is depleted of electrons. And so we refer to it as the depletion layer of width W. Okay, the width of this layer, where there are no electrons, no free electrons there, is width is W, where W is known as the depletion layer or space charge layer, because there's a charge that is there due to the positive charges that are left behind. A positive value is there. So this is the situation in equilibrium, and when we look at that, the built-in voltage, if we analyze it, that is going to be established, will be given by phi m minus phi n. We can see that shortly also, by E. If you consider two metals, we will see this to be the case much more easily. But the same idea is here also. That difference in work function that is there between these two is what will be the built-in potential, or built-in voltage. And potential accordingly is simply phi m minus phi n. The built-in electric field is non-uniform. And is maximum at the interface. Okay, the field that is there, this one, is a non-uniform field. It increases, and it's the maximum at the metal semiconductor interface. So at equilibrium now, we have EFM is equal to EFN. The two Fermi levels are equalized. Now we have to keep in mind that in the bulk of the semiconductor, okay, nothing has changed. It is only in this small region close to the interface that we have experienced changes. What is the change that we have seen here? A layer has been created which has got fewer electrons. Now, when we think in terms of the carrier concentration N and with respect to the Fermi level, if there are fewer electrons somewhere, say if that is EC and that is EV, I've got some situation where there's, I'll draw two cases. There's a standard N-type material with certain carrier concentration with EF this height. Now, I remove some electrons. What will happen to this gap? It will increase, right? So let's draw it here roughly. So this is the case where there is fewer electrons, that the EF has shifted with respect to EC. And what I'm saying is that the depletion layer reflects the situation, because there are fewer electrons there with respect to the bulk. Actually, all the free electrons have been taken out of there. All we are left is with that space charge. And then the rest of the semiconductor, nothing has changed, where there are more electrons, and therefore this gap is smaller. So what that means is that in part of the semiconductor, we've got the Fermi level closer to the conduction band edge, and in the depletion layer it's farther, which implies a bending of the bands to maintain the continuity. So what that will look like is like this. EC in the bulk of the semiconductor remains where it was, or EF I should say, remains where it was with respect to EC, whereas in the depletion layer, because the carrier concentration has decreased, effectively there's no free electrons there, there is a larger change. Okay? So effectively all the bands get bent, and we can redraw this then. After contact, here's the vacuum level, here's the metal work function or metal Fermi level, and then we have the situation that the Fermi levels are the same in both now. Okay, something like that, and then vacuum level is also. So here we have EFN now, EV, EC, and the vacuum. So this is after contact. Because of the fact that equilibrium is established, there is the two Fermi levels are aligned, and when equilibrium is there, this is my depletion layer with W. Okay? And when we look, yes? Because the amount of energy that it takes to remove there hasn't changed. I'm maintaining continuity.
Shouldn't it increase because now the semiconductor has a positive core, so
No. That is only at this interface. And then you do see that with respect to the Fermi level, it has increased. But in the bulk, nothing has changed. So how much energy it takes to remove an electron from the bulk remains unchanged. And that's why we are the whole thing is bent. Right? Now when you look at it, this is the built-in potential, which we'll see is E V naught. Built-in voltage is V naught, and built-in potential is E V naught, which is given earlier. We had written it as phi m minus phi n. This is phi m, and this is phi n. Okay, so the built-in potential is E V naught is equal to phi m minus phi n. So when electrons want to go from the semiconductor now into the metal after equilibrium has been established, they will have to overcome this barrier, and that's why they have stopped going. Equilibrium has been established. On the other hand, electrons which want to go from the metal to the semiconductor have to overcome this barrier, okay, which we will refer to as phi b, or the barrier height. And phi b turns out to be what? What is this distance? What is this? From the bottom of the conduction band edge to the vacuum level in a semiconductor. We just looked at it earlier. No, that is to Fermi level. Chi, very good. That's chi. So phi b is nothing but phi m minus chi, because that hasn't changed. You see, that's when I was discussing chi earlier, I told you that Fermi level may change with doping, but chi, so therefore work function can change with doping, but chi doesn't change. Chi is from the bottom of the conduction band edge to vacuum level, and that has remained constant. So now we have the situation that if electrons want to go from semiconductor to metal, the barrier that they face is EV naught, phi m minus phi n. From metal to semiconductor, if they go, they face a barrier phi b equal to phi m minus chi. And it is this difference that fundamentally explains the behavior of the Schottky junction. Okay? and it is obvious that phi b is greater than EV naught. Can you see that from the picture? Phi b is this distance, but this one minus this, whereas EV naught is a smaller distance from this level to this level, which is simply phi m minus phi n. So we can also write phi b in terms of the EV naught by there. Phi b is equal to EV naught minus, or I'm sorry, EV naught plus EC minus EFN. That is the amount by which phi b is greater than EV naught. If you look into your figure, phi b is equal to this distance plus this distance, which is EC minus EFN. This is the situation when equilibrium has been established, the metal has been deposited on the semiconductor, electron flow and all that has taken place, equilibrium is established, and we know the barriers for both ways. Now, in open circuit conditions, I'm not connecting anything to the ends of the semiconductor. I'll refer to open circuit simply as OC from now on. Okay. We're going to see what will happen. Is there any current flow in this system? With nothing connected to it, it's in equilibrium, so there is no net current. And yet, because of energy, some electrons are going to cross this barrier and come this side, and some are going to cross and come this side. But because it's in equilibrium and there is no net current, what that implies is that the numbers that are crossing from here are equal to the numbers that are crossing from here, right? So we can write the current in each direction, J1, which is the current for the metal to semiconductor, in this open circuit condition, where it is simply by thermal emission over the barrier, is equal to some constant times T squared exponential minus phi b by kT. Not going into the details of this thermionic emission theory, basically. This is what we will get roughly. Different books treat this slightly differently, but the current density J1 for metal to semiconductor is over the barrier phi b. On the other hand, J2, which is the current from semiconductor to the metal, is equal to Ct squared exponential minus EV naught by kT. The barrier now is EV naught for going in this direction. So in equilibrium, the net current in open circuit is equal to J1 minus J2, or depending whichever way you define it, is 0. J1 minus J2 or J2. That means they both are equal. So this is the equilibrium condition, by which we mean it is open circuit in the dark. Because we know that when light of the appropriate energy falls on semiconductor, even if it's open circuit, things could happen. But in this situation, there's no light, and this is in open circuit condition. Now the question is, what happens when I bias this semiconductor, which has got a contact on it? What will happen to it?
So in case of equilibrium, phi b equal to EV naught.
Yeah, actually, I have to be careful. This constant here is not necessarily the same constant. That is where the difference will come. Okay, there is some constant term that is not the same. We can probably write it as C1 and C2. Different books treat it differently. But if effectively, phi b is not equal to EV naught. That's what I just showed. Phi b is greater. But there is some difference in that constant. It's some constant multiplied by the barrier. It is related to the fact of how many electrons may be available on this side to go across that can make the jump. You see, it is the probability of the jump over a barrier phi b versus the probability of a jump of how many electrons here making the jump over the barrier EV naught. Okay. So the barriers are not the same, as I just said, but the currents are same because of the probabilities of how many electrons are available to make the jump. There's a lot more in the metal than in the semiconductor, so it turns out to be the current is the same, even though barrier heights are, the barriers are different in both cases. Now when we bias it, we can do two things. One, the first case that we will see is forward bias, where we connect this to the negative terminal and the metal to the positive terminal, right? This is the situation of forward bias. I've got the metal and the semiconductor. And when I do this, the way the field that is now going to act on this, the externally applied field, will oppose the built-in field, right? And so there is a lowering of the barrier due to this. So in this case, the applied V opposes V naught, the built-in voltage. And so we will get a shift from in the barrier from EV naught to EV naught minus V. So for semiconductor to metal electrons, we have a lower barrier. But for metal to semiconductor, the barrier remains the same at phi b. Nothing has changed. Chi hasn't changed, phi m hasn't changed. Okay? So nothing has changed for the current which is going from the metal to the semiconductor. But in the opposite case, we've got a change. So J2, I think this is how we define, and J1 was related to this. J1 remains unchanged. J2 will increase. Barrier has lowered, right? So when we draw the diagram for this now, the same kind of a diagram if we draw, got to be careful on this one. I'm not very good at drawing things. This barrier now that we have is EV naught minus V. It has shifted from EV naught because the field that is acting externally connected to this opposes the one that is the built-in one. This barrier, on the other hand, phi b, remains unchanged because chi remains unchanged and phi m remains unchanged. So under these situations, we have J2 then is equal to a constant times T squared in the forward bias condition, exponential minus E V naught minus V by KT, some constant there. J1 in the forward direction is equal to, it remains unchanged. Okay? So now we will have a net current J in the forward direction, which is given by J2 minus J1. And this is where different books do different tricks. As you pointed out, if we take the constants are different, that will account for the fact that these are not equal. So in some books, they take this constant to be the same. Here's an approximation that is being made. And then this is still different, even though you know that there are two different constants, you take it to be the same. In other books, they'll take these two constants to be different, and at this step, when you do the J2 minus J1, you should get C2 T squared exponential minus E V naught minus V by KT minus C1 T squared exponential minus phi b by kt. So the J forward current can be written as, thank you, I was absolutely muddled on it. You're very helpful, thank you. C2 t squared exponential minus E. I was wondering about that myself, but I couldn't grasp it this morning. And what we are doing is that the J1 in the forward direction, which is strictly C1 t squared exponential minus phi b by kt, we have the equilibrium equation where these two are equal. So we can substitute now for this as minus C2 t squared. Very good. Thank you. I had a feeling I was wrong somewhere, but I couldn't puzzle it out at 5:30 in the morning. So now we've got the same terms. We don't need to play with the constants at all. Thank you. C2 t squared exponential minus EV naught by kt exponential EV by kt minus 1. Very good. Okay. Under forward bias, then we've got what the current flow looks like. So we can then put this whole term here as J naught. Just clubbing it together because it doesn't have a voltage dependence, though there is a temperature dependence. The voltage dependence is here. This doesn't change. So we can rewrite this equation then as J in the forward direction is equal to J naught exponential EV by kt minus 1. Okay. This is the where J naught is known as the reverse saturation current. And you can see why. Right? When it saturates, it has this value, which is simply the reverse direction saturated current value. So this is if we now plot the characteristics in the forward direction, we'll get an exponential dependence with voltage. We can do this for reverse bias now, and we will look at the case where we apply a reverse bias. Now in this case, the field enhances, the applied field enhances the built-in potential, and so we get a larger barrier going from one direction to the other. In the other case, the barrier reduced. In this case, the barrier will increase. I'm just drawing it quickly. Something we have now a larger barrier. Okay, basically now the barrier has added on, and we have EV naught plus the reverse bias. Okay, if we refer to reverse bias as V subscript R, then this is the situation. So again, now we have in reverse case J2, which is for semiconductor to metal, is now C2 t squared exponential minus E V naught plus VR by KT. J1 hasn't changed. All right, it is still phi B. So we can write that again as CT2 squared right, because J1 is equal to J2 still in the equilibrium case. I've just made that substitution directly. Now when you think of this, V naught, which is the built-in potential, is some kind of a fraction of a volt. Millivolts kind of number. VR, which is the applied bias, is a few volts. And when you compare these two, you can see that J2 in the reverse direction is much, much less than J1. You've increased your barrier drastically by applying the reverse bias. V naught is a small number, VR is few volts, and so when you applied the reverse bias, J2 has become very, very small. So simply what you're getting current flow is related to J1. So in the reverse bias case, J reverse bias is simply going to be J1 reverse bias. This other term is very small. And so we will get it's equal to C2 T squared, or if we express it in terms of phi b, C1 T squared exponential minus phi b by KT, or the other way, CT2 squared. All right? So now we are in a position to draw the IV characteristics for the Schottky junction for both reverse and forward. And when we do that, I'm going to draw current versus voltage instead of current density, which we obtained, simply a matter of multiplying it by A. In the forward direction, we will see some behavior like this, which has the exponential behavior, and say some milliamps or something like that current flowing. In the reverse direction, I'm changing the scale, though I'm plotting it on the same diagram. We are talking of, say, over here is 10 microamps. Just to show on the same scale the magnitude difference. Nanoamp kind of currents flow in the reverse direction, yeah, and milliamps in the forward direction. And so this behavior is what is known as our rectifying behavior, which is what one of you mentioned right at the beginning, that in one direction it allows current to flow, in the other direction it doesn't. We have some kind of a turn-on voltage of about 0.2 volts. Beyond that, it rises sharply. Now, when we compare the different equations, it is possible to describe both forward and reverse bias with the same equation. Yes, long as we substitute V by, in that case we can use J is equal to J naught exponential minus, what is it, exponential EV by KT minus 1. Can apply in both cases as long as you substitute the reverse bias here. Okay, this is a very large term that you get in minus, and so effectively it will saturate back to this number. That's why it is known as the reverse saturation current. Also, V in the forward direction, if it is greater than KT by E, okay, which at room temperature, KT by E we are talking about is something like 25 millivolts, 0.02, sorry. So if the forward bias is more than about 25 millivolts, then our equation J is approximately J naught exponential EVF by KT. In other words, that minus 1 term there can be dropped if you're talking of forward biases larger than about 25 millivolts. The whole argument can be made for p-type also. In other words, for p-type, the Schottky can be created if phi m is less than phi p. In this case, we'll get the opposite. The holes will behave with this rectifying, same kind of behavior we'll see. Band will bend down. That's a barrier for the holes. Now, this theory, which is thermionic emission theory, is a very simplified version of what actually occurs. In many semiconductors, if we look, we will see a completely different behavior. And I don't have time to go into all of it, but I'll point out a couple of things quickly. We have this situation roughly where the metal semiconductor, the barrier is there, and this one is phi b. Now, one would presume that as long as which is phi b is equal to, in the case of n-type, phi m minus chi. So, for the same semiconductor, if I use a different metal, which has got a different metal work function, one would suppose that phi b changes. And phi b is something that we can measure experimentally from a current voltage curve and things like that. So, if I measure phi b and plot it versus phi m, I should expect a straight line. for the same semiconductor. The reality is that sometimes that is not the case. We may almost get that instead of phi m, or rather phi b versus phi m, instead of getting some kind of a straight line, I may end up with something that's flat. That means no matter which metal I use, phi b does not change. And there are many theories that are related to it, but basically the idea is that due to what are called surface states and defects, that means there is some kind of other levels that are here which we haven't even thought about. We're talking of a perfect metal semiconductor interface. There are other defect states that are introduced here which effectively pin the Fermi level to some value. And then that's already bent, it's pinned. And there are so many states there, the defect density is high enough that no matter which metal you put, it will not basically alter this band bending. Okay? That's known as the surface states, metal-induced gap states, that's called MIGS, or surface state theory, where we talk of the idea of Fermi level pinning. So in some semiconductors, for example, gallium arsenide, this is more or less true. And it is dependent then on how we have prepared the surface and so on, because the defects that are introduced are a consequence of all these conditions. What we see here, the phi b is equal to phi m minus chi, is an ideal case where there is no interaction between the semiconductor and the metal. It's perfect interface, and based on that theory, it's what is known as the Schottky mott theory, what we just described, where phi b depends on phi m. You may also have reactions when you deposit a metal. We have not considered any of those cases. Briefly then, for ohmic contacts, I don't know how much time I have left because we started a little off. As I said, we want that the characteristics should be linear, though in reality some degree of non-linearity is also acceptable, as long as the second condition, that contact resistance is very low. In other words, the contact does not limit the current flow. Most of the resistance should be due to the semiconductor rather than due to the contact. And in this case, for ohmic contacts, again taking the metal semiconductor situation, phi and an n-type, phi m should be less than phi n. For Schottky, we saw it as phi m greater than phi n. In the case of ohmic, this is all ideal theory. We've got phi m less than phi n. For the metal here, we have then the two of them being brought together. So this is phi n then. And chi as before is here. And when we bring these two together then, just as we did in the earlier case, electrons will flow from the metal to the semiconductor, and electrons will accumulate in here, and gradually it will start opposing the further flow. Okay, when an electron has gone from here to here, effectively it's left behind from a neutral semiconductor, neutral metal, it's left behind an effective positive charge. And same way here, when electrons flow down to this level, it accumulates here. There is an effective negative charge building up. So we have a field that is set up now after contact in this direction. So after contact, the situation that we have then will look a little different in this case. That's the vacuum level, and okay. The opposite direction the field is set up. And now we see that electrons have accumulated here. Note that the Fermi level is in the semiconductor, I mean in the band, conduction band. And here also there's lots of electrons available. Here also there's lots of electrons available. There's hardly any problem for electrons to go back and forth. So basically this area is no longer known as the depletion region. What we call this is now the accumulation region. So electrons have accumulated there. And so without any opposition, electrons can flow back and forth. The same kind of thing would be true for p-type, where we would have the opposite condition that we have. So for p-type we would have phi m greater than phi p, in which case we will get ohmic contacts. Ideal theory. Reality is very different. I wanted to take up an application, one or two applications of this, which I may probably do the next time, namely the solar cell, for example, which is a photovoltaic device or a photodetector, and maybe some thermoelectric devices, before maybe we'll do PN junctions and so on. Okay? So this is where we'll leave it for today. These are the two main types of behaviors that you would see, either linear characteristics, IV, ohmic contact, or the rectifying behavior where we have Schottky contacts.